Ilalaban kahit kanino, oo, simple lang ako at malabo mong magtipuhan. Kaya okay nang kahit sa FB mo lang mapusuan. Kasi di na mapigilan ng sariling mapaibig sa iyo. Ano ba to? Gusto ka laging
So I have here a problem regarding our topic earlier about SP3 hybridization and the formation of uh, tetrahedral bonds using carbon as our central atom. Okay, so the question is, draw the tetrahedral representation of tetrachloromethane or carbon tetrachloride using standard convention of solid, dash, and wedge line. Okay, so how do we do that? So we already knew earlier that carbon is a tetravalent carbon. That means that if carbon is our central atom, then it can bond to 4 different types of atom. Okay? So 4 different types of atom. So we can now draw the line bond structure for this. And we knew that chlorine, how many chlorines are there? There are 4 chlorines. So it would be that chlorines are actually bonded directly to carbon. The 4 chlorines are actually bonded to the carbon. Okay? And remember that each bond contains 2 electrons, one for the chlorine and the other one is for the carbon. Okay, so if there are 4 bonds, then this will suffice your electron rule or the octet rule. So that means there are already 8 electrons that are surrounding your central atom, which is the carbon. And remember that 1 electron is coming from the chlorine and the other electron is also coming from your carbon. Okay? So that means that if the valence electron of carbon is 4, so the valence electron of carbon is 4, therefore, all of its valence electron are used up to make a bonds. Okay, so 1, 2, 3, and 4. Okay, how about for chlorine? How many valence electron are there in one chlorine atom? According to your periodic table, this is halogens, that is group 7A. So therefore, there are 7 valence electron. Okay, so for chlorine, it only bonded to carbon with one. The chlorine only shared 1 electron to the carbon. Okay, so therefore, if there is only 1 electron shared by the chlorine, that means that there are 6 electrons left. Okay, so only 1 carbon is being shared by the chlorine to the carbon. So there's only 1 electron that is being shared by the chlorine to the carbon. So there are actually 6 electrons that remains after the bonds. Okay? And this 6 electron is actually the lone pair of your chlorine. So since it is a lone pair, then there are 3 lone pairs for each of the chlorine. Okay? So each of the chlorine will have 3 lone pairs. Okay, I will just use that 3 lone pairs. Okay, 3 lone pairs that will represent your 6 electrons. Okay, so 2, 4, and 6. However, this is only the line bond structure. Okay, we are asked to get this standard convention for solid, dash, and wedge line. Okay, so how do we do that? So we want to convert the line bond into a standard convention for getting the tetrahedral or the 3-dimension representation for the tetrahedral of the molecule carbon tetrachloride. Okay, so how do we do that? So carbon is our central molecule or central atom, I mean. Okay, sorry for that. And we have a solid line. Remember that we have 2 solid line that represents a band in plane. Okay, so that will represent a bond in plane. Then we have a wedge line, which actually represent a bond that is in front of the viewer, or in front of the viewer, or it actually preceding in front or out of the page. Okay, out of the page. And we have also the dash line that will represent a bond that is preceding behind the page, or behind the page, or at the back. Okay, so this will now be the representation for the 3D or three-dimensional structure of the tetrahedral for the molecule carbon tetrachloride. But don't forget your lone pairs for each of the chlorine. Okay, so don't forget about that, because lone pairs are very important. Okay, then we're done for this molecule. So this is now the three-dimensional representation, or the standard convention for the molecule carbon tetrachloride. Okay, so we're done with draw the tetrahedral representation of chloromethane. So the next would be, why do you think a CH bond is longer than an HH bond? Okay, so what is the CH bond for methane? That is actually 134 picometer. Okay, so 134 picometer. While for, so this is 134 picometer. That is 134 picometer. Okay, I already discussed that earlier. While for HH bond, that is only 74 picometer. So why do you think that the CH bond is longer than an HH bond? Why? First of all, HH bond is what? HH bond is smaller, or smaller than your CH bond. It's because how many electrons are involved here? There's only one electron for the hydrogen and one electron for the another hydrogen. And the nucleus of this it contains one proton and the other one proton. Okay? And remember that your hydrogen and your hydrogen, both of them have the same size. Okay? So they are both spherical, and since they are the same hydrogen, so they could have the same size. Okay? So this is now its maximum this is now its bond length that leads to its maximum stability. Okay, well for CH bond, remember that your carbon is actually bigger than your hydrogen. Okay? And also your carbon contains a lot of electrons and protons compared to your hydrogen. So this will make your bond longer because of repulsion. Okay? Because since your carbon is much bigger atom than your hydrogen, so there are still electrons on its 1s orbital, because each 2s orbital are actually involved in the bonding, and the 2p orbitals for carbon also involves in bonding. But for 1s, it doesn't involve in bonding, so basically it's just there. Okay, the electrons are just moving there, and also the nuclei or the nucleus of your carbon contains protons. So this will make a stronger repulsion towards your hydrogen. Okay, because there are a lot of proton that is actually in the nucleus. So there in the nucleus of the carbon, there are actually 6 protons. Okay, your carbon has 6 protons. 6 protons, and you only have 1 proton for your hydrogen. Okay, and since there are a lot of protons that is actually in the carbon, this will also repel to the nucleus of your hydrogen. Okay, although there are only 2 electrons that is present on the 1s orbital, but it will not cancel their charges, because there are a lot of protons that are actually present in the carbon. Okay, so that means that it will tend its length or bond length to be much longer away. So it's too far, not really too far, but it has its bond a maximum bond length of 134 picometer compared to 74 picometer for the HH bond because of actually repulsion. That's why your tetrahedral structure for methane it 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 is tetrahedral because of what we call the BSEPR, okay, or the valence shell electron pair repulsion. Okay, so it is governed by this theory, valence shell electron pair repulsion. So in order for the CH bond or the carbon and hydrogen will in order for them to reduce repulsion, the carbon or the structure of the molecule will tend to rearrange itself in such a way to reduce repulsion. Okay, so that's it.